My name is Peter Feiler. Two minor facts about me. I have been at the SAE even longer than John Goodenough, 30 years. And the second one, I have a second name, and that is I'm known as Mr. AADL. I have been dealing with AADL as a standard since we started in 1999 together with Bruce Lewis from Amerdek. It's based on research technology that came actually out of DARPA programs. But Bruce realized in order to make it reality and get industry to use it, we needed to take the standards approach, and we worked with the SAE to accomplish that. In this talk, I'm focusing on a workbench around the AADL language, and the focus of the workbench is to provide you with the capability to do what we call virtual system integration. That is, look at the interaction of the parts of your system as early as possible in the process, rather than doing it at the time you do system integration. First, I'll give you a couple of slides on challenges. Second, go into the workbench and the virtual integration concepts, and then talk about some of the capabilities in the workbench and how it's being used in various projects. One of the things we are facing, and here I'm focusing on the avionics community, but you're familiar with that in the news almost every day. There's now something about software messing things up, whether it's in cars, in robots, or whatever else you have. The one on the left is actually something that happened several years ago. The aircraft all of a sudden went into a 20,000 feet nosedive, and when they did the accident report, the circle that is highlighted there, it says it appears to be a unique event. That to me indicates they had no clue what was going on. But in reality, what was happening is that some parts of the system malfunctioned. As a result of that, the system went into various kinds of failure modes, and it was because of mode confusion. Faulty data was still being sent around within the system, even though it was supposed to not happen. The second one is a little more recent and is actually even a little more interesting, and that's the one that happened with the 787. Was in the news in May of this year, where the FAA issued this thing about saying don't leave your aircraft on for more than, 240 some days. And so what was going on in this case? In both cases, it was software that was involved in this. In this case, it's even interesting because of the following facts. First of all, from the requirement side, there was not a well-specified requirement about how long an aircraft will have its power systems in operation. Everybody was assuming, since they need to do a full maintenance cycle every 6 months, that at that time power systems would be shut down. Well, it turns out that's not always the case. Secondly, they were keeping track of time by keeping time ticks, and they were using a variable of a default size of 32 bits, and the time tick of a granularity that the operating system happened to give to them. And as a result of that, that variable wrapped around into negative numbers after 246 days. Not only that, we also have a very nice example of a software design error. The power system is quad redundant, but because it is a software design error, we lose all of that redundancy because we have a symmetric error in all 4 copies. So all 4 copies of the power system would have shut down in mid-flight. It is nothing as compared to physical systems where you have fatiguing and so on. Different instances of the same system would fail at different times, and then you have actually higher reliability than what we get in software. Oops, here we go. So one of the things that we're realizing that as we do these embedded software systems, we have now a new class of hazards that traditional system safety analysis doesn't address. Typically, system safety analysis is done early in the process by system engineers. They worry about all of that stuff. And then we slowly move and go into the software side and have not considered the contributions that software makes to the reliability of the system as a whole. This is a slide that John Goodenough already showed you. The main point that I want to make again is what we have is it's the interaction between the different software parts that is the main problem. When we write the code and do the testing, we are actually pretty good on the individual units. It's the interaction part that then leads us to this need for virtual system integration. Can we detect these issues early in the process? And they tend to be these non-functional properties like performance, like timing, like reliability, and so on. I'm pushing one button too low. And I'm For that purpose, we developed this language called AADL, Architecture Analysis Design Language. It's done under the SAE International. That's a very interesting community because most of the members are people that are in need of technology and are looking for solutions. So they are not interested in pushing a particular technology like you have in some other standards organizations. And so having that really helped us focus the standard to become something practical. We actually had to write a requirements document for the standard before we could start developing the standard. And it needed to be signed by 6 member companies so that all their needs are reflected. And that's what made AADL a practical language and moved forward. As it was designed, we wanted to focus on characterizing embedded software systems. For that, we are not just interested in the software architecture as a design artifact, namely how do we organize things in modules or packages, but on the software side, what's more important is to characterize the runtime architecture, your task and communication architecture, because that's the one that drives your non-functional characteristics. And then we need to map that onto hardware platforms so we can actually determine whether we achieve logical or physical redundancy, achieve our performance. And we also need to deal with the fact that we are interacting with physical systems, both at the logical level between software and the physical system, and physically between the physical sensors and so on and the computer hardware. And so AADL was designed specifically to cover all 3 of those aspects. As we have defined AADL, we put semantic meaning into the various concepts so that analytically we could drive analysis along multiple dimensions. Some of them are built into the core language, and some of them are added in through extensions to the standard we call annexes. One example of that is the ability to associate fault information with these architecture models. Once you have that, you can now have an annotated architecture model, and from that you can drive all your different analyses by actually generating the analytical model and then feed it into, in many cases, existing analysis tools. By doing that, we now have a single source of information to drive our development process. What that means then is the following. If, for example, I have my system and I need to make a change, for example, increase the encryption from 128 to 256 bits, I can make the change on the security part of the system, but there is a side effect of that, namely you have higher CPU time, higher processing demands. As a result of that, you may have to do more computations, has some implications on your latency. The latency may affect your temporal correctness, so you need to worry about the data quality. And as a result of that, you may have some new hazards that you hadn't thought about before that you now need to address. By driving all of this, you make an architectural change, and then we simply revisit all these analyses in an automated fashion. We actually can determine the side effect of these things. The second part of it is to say, as we do that and do it model-based, we now, instead of having a traditional V where we do development on the left-hand side and the verification or testing on the right-hand side, we now have a double V. First of all, on the development side, we continue to make development decisions on the right-hand side as we calibrate and configure systems that we test. And on the other hand, we are now building up evidence or verification that our design has fewer errors by doing some of these analytical verifications early in the process. And as a result of that, we can now discover problems that currently make it all the way through unit test and past unit test, and it's 80% of all system problems go that way. We can catch some of these earlier. And it's this kind of thing that got interest in this system architecture virtual integration initiative that was mentioned by John early. Now I'm going to give you some samples of what the tool bench can do, and then we will go into a couple of examples of where that was used. The Workbench itself deals with obviously all the notational aspects, AADL, the core language, EMV2 stands for error model. The version 2 that just came out, it's the fault modeling capability. There is an ability to do refined behavioral specifications so we can drive model checking type of activities. The notation itself is a strongly typed language. It's actually, for those of you who still remember something called ADA, I don't know how many of you still know that name. It is a very good language, strongly typed, and really allowed you to do highly reliable software. We try to follow that pattern in AADL as well. It's a strongly typed language. So there's a lot of consistency checking in models that comes for free where you don't have to do anything as compared to UML-based models where you would have to do a lot of that kind of work yourself through consistency checking. There's also team management that comes with the environment because we built a tool set on top of Eclipse, so we didn't have to do extra work. Then some of the analysis that I showed you in the diagram, we actually have implementations of those. The idea was to show to people that we can deal with all the different dimensions, and for people then bring in some of their own technologies and hook them in as well. But there are some analyses that are quite interesting from an end user perspective. One of them is latency analysis, and I will talk a little more about that, and a couple of other ones. Some of them are very practical ones that are as a result of working with industry initiatives like SAVI. The functional integration is one of those, and that has to do with when you go through an RFP type of process and your subcontractors propose systems back. If you do that in the context of an AADL model, I now can, as a system integrator, already put the models together and do some consistency checking, for example, to make sure everybody agrees on the same measurement unit. Everybody agrees on the same size for integers, for example. Issues that are very common, low-hanging fruit type of things, and we can go beyond that. One of the things we have added more recently is make the tool set more user-friendly for end engineers, because in the first round, it is the reference implementation of the language. It was a prototyping platform. We wanted people to be able to build and add in new capabilities. It has become a research transition platform for recent DARPA programs as well. But more recently, we added capabilities, and you'll see some snapshots of that, role-specific workflow and making things more user-friendly. We also brought in some software that we now release as part of OSATE that was actually not developed at the SCI, but outside. Three examples are shown here that we have integrated in. One comes from Spain, a system called MAST. It does certain kind of scheduling type of work. The top two, Resolute and Agree, were developed by Rockwell Collins and have been used in DARPA programs. They are now also part of this release. And then there is also code generation capability that automatically generates runtime executives or operating system configurations that can be done from AADL, and we have that supporting several real-time operating systems. In terms of the front end, people want graphics. The language itself is has a graphical representation and a textual. When you do the graphics, then you can get additional information either as annotations on graphics or in a table-based view, as is shown at the bottom here, where you can then characterize, for example, your compute execution time, what the period and deadline is, and things like that. As we do that, there's context-sensitive data entry, there's quick fix type of stuff, the kind of thing that you're used to from other environments that deal with various kinds of languages. The more interesting part is end-to-end latency analysis. What you typically find is when people think about end-to-end latency, and that's what they find in repositories, is the fact that you have sampling latency, compute latency, and communication latency. And in reality, when we implement all of that in software, there's many additional contributors to the latency that come from the software side, whether you use partitions, when do you communicate the data, do you run sampled or not, all those kinds of questions. The analytical capability that we have understands all of that, so depending on how many decisions you have made in your architecture, we already can give you feedback early in the process and say, by the way, even at time of requirements specification where people say we will use a ring 653 type of thing and do a certain kind of mapping of saying different suppliers will be in different partitions. From that fact, we can already determine whether you are missing your end-to-end latency requirements or not. And so here's then an example of that. We take advantage of an end-to-end flow specification that comes with the language. And then when we generate reports, it gives you the end result, but it also shows you the intermediate steps, because in many cases, people don't believe us the numbers, but most of the times what happens is they forget about the fact that there is a certain contributor. So we give you a full record for what's happening on that front. In a similar way, we have taken research at the SCI and other places. In this particular case, we are highlighting some scheduling research that has happened here with Theo Denise's group, multi-core scheduling and mixed criticality scheduling. As that has been now integrated into the Workbench as well. There used to be algorithms that were working standalone based on data tables handed to them. Now we are deriving these analysis from data that comes from actual AADL models, and behind the whole thing is obviously all kinds of theory and all that, but you as an end user just specify information, additional information in your AADL specification, whether it's visual, graphically or in textual form, and you can drive it out. In terms of safety, interesting thing on that front is even big companies like Boeing that do commercial aircraft can only afford to do a system safety analysis once every 3 or 4 years because it's a highly labor-intensive manual process. Often many of the architectural decisions have been made. You're just showing that you haven't missed any of the major things. By automating that process, again, annotating architecture models with hazard information and making use of the fact that we already know which parts talk to which parts, which pieces of software run on which pieces of hardware, we can derive what are all the propagation paths and then automate this whole process of fault propagation. So we can now explore your design space, and one of the persons that has been using that is Myron Hecht from Aerospace Corporation on satellite systems with JPL. So he now explores various design alternatives for satellites and deals with as many as 26,000 failure modes and 25 level steep type of thing, which is if you do it manually, you would never be done. And his comment is, in the current process, there are only 2 people that read those FMEA reports, the 2 guys that write them, because everybody trusts their their knowledge. Well, this is the thing that we want to change. So coming to a closing, I have just 2 more slides. One of the areas that it actually has been used as well is security verification. There is a DARPA program called HACMS, whose focus was high assurance in terms of the security arena. A team that included Rockwell Collins in a project called SMACM here was doing that for a drone type of thing, and they applied these technologies that some of it I show you in a moment, but also includes automatic code generation and verified kernels, such that after 16 months, the Draper red team that was supposed to be able to break into the systems in the 6 weeks period was not able to break in because they covered all the low-hanging fruit holes. And it's only the more sophisticated things that are timing related and so on. Those other guys don't know how to get their hands around yet. But overall, what the primary thing is, you have some specification of some security characteristics, like making sure that when a command is issued from the pilot to a certain device, that along the complete path, all of it stays encrypted. And as it's mapped onto particular pieces of hardware, that the hardware itself doesn't have holes in terms of maintaining that encryption. If you have that specification, we can apply it to the model at various levels of detail and then get reports out as to where we have potential problems. And then you work those until everything is green, which is shown at the bottom. So in closing, AADL is interesting as a standard language. There's actually a standard suite. There's several things around it. It has strongly interacted with the research community in 2 ways. We started out with research work to turn it into a standard. And then at the same time, it has become a platform for people that are doing research to do it on top of it. And the DARPA programs are some examples, European projects as well. More interesting, as soon as the standard came out, we applied it in various projects. And I'm showing some Army projects doing some initial pilots. A health monitoring system, and we did some work also with NASA, for example, with a reference architecture for unmanned platforms. I mentioned the System Architecture Virtual Integration Initiative. That's where Boeing, Airbus, Embraer, Honeywell, Rockwell Collins, all the suppliers, NASA, FAA, and the DoD are all working together to figure out how to improve the situation that we have, namely our software cost skyrockets. And the only way they see is this notion of virtual integration, and they bought into using the technologies that you see here. More concretely, also in the Army context, there's a program called JMR, Joint Multi-Role. It's a tech demo program that feeds into future vertical lift for rotorcraft. And we are currently in the phase of applying what they call architecture-centric virtual integration with the contractors to gain the experience on how to adapt their processes to do this kind of work so that it's mature enough to be used when we start with future vertical lift. And finally, as we do the work as a standards committee, we are not doing that in isolation. We actually work with various other committees. Some of them then use the technology. Early on, it was OMG interested in kind of competing with us and did something like MARTI, but that became such a heavyweight standard that it died under its own weight, more or less. And then on the other hand, we work closely with ARINC 653. As those standards made a revision, we then adapt to support that particular standard. We work with the networking standards community, with S18 from SAE, that's the guys that do the system safety work. They're currently going through a process of making their practice model-based, and they're bringing our approach into the picture. And most recently, we also worked with some of the regulatory agencies like Underwriters Laboratory, NRC, and FDA, because they, from their end, are interested in improving the quality of these systems as they become more software-based. And with that, that's the end of my story.